Yeah, my name's Fred Vocasek, just quick history. I grew up in southeast Nebraska, close to Beatrice, or about halfway between Beatrice and Lincoln, if you're familiar. Worked as a degree in agronomy, worked as a field agronomist in northeast and central Nebraska, and then migrated down to southwest Kansas. I'm been there, well, 40 full-time years and now a year and a half part-time. So that kind of explains the senior, the hair color. This is just illustrating ServiTech. The blue circles are where we have staff located. And that's kind of changed over the years, but we have staff from the Front Range of Colorado all the way to Mississippi. So we cover a pretty wide geography, and it's pretty diverse. We go from corn, soybean, we have sugar beets, we have potatoes, we have those kinds of things. Slide. We have, our headquarters is in Dodge City, Kansas. That's where we started. We have a laboratory there. We have a laboratory in Hastings, Nebraska, which is probably the one that you're probably, dealing with, and also in Amarillo, Texas. And we do roughly half of our business is soil testing, about half of it is feed testing. You might say our territory goes from Texas all the way up into the Dakotas and over into Montana. So we cover a pretty, and even a little bit of international business. So anyway, if I were sitting in your place, I'd say, okay, what's this guy from southwest Kansas going to tell me about soil pH? You know, he lives there where we got all those high pH soils. You know, what does he know about it? So I want to take you for a minute to Haxton, Colorado. And Haxton gets about half the rainfall you get here in this area. It's been farmed since probably the 1880s or 1920s. Started out as wheat, fallow wheat. Now we have continuous corn. You know, we have irrigation, but even on the dry land with the genetics we have, our dry land corn, we have continuous corn. So Dave Green was our territory manager in that area. Dave's, like me, one of the grand old men. And he went through, and what he did here was he put together about 30 years worth of his soil test history. Look at the pH. And what he did when he did that, he went out, and what he did was he sampled here some pastures. These are 4 or 5 different fields. He sampled a pasture next to them, thinking that was the native condition. And what we're seeing as we go to the 80s, 90s, 2000, 2010, we've got about a 30-year long, slow slide from about pH of 6.5. We're getting down 5 and even lower. One of his guys a few years ago sent me a grid map on a dryland wheat field. The high pH was 4.7 and the low pH was 3.8. So this is something, this whole pH problem, it's something that's developed over the last, when I moved to Kansas, south central Kansas, north central Oklahoma, it became a huge problem. Now we've got it not in every area, but many areas. That's one of the challenges we look at, is we're seeing acidic soils develop. It's also a problem in Pacific Northwest and Montana. They are fighting it. So I'll talk about that a little bit later. Go ahead. So just a quick review. When you talk about pH, we're talking about a scale of 1 to 14. And we're measuring the acidity or alkalinity of a water solution. Now, neutral, this deionized water will have a pH of 7. As we get below, it's acidic, get above, it's alkaline. And what we're measuring, if we have the water molecule, H2O, it'll dissociate, a certain number of them will dissociate into a hydrogen ion and a hydroxyl ion. And so what we're measuring is a hydrogen ion concentration. So that's what the H in pH represents. The P means a logarithmic scale, it's base 10. So what that says, each unit change in pH is a 10-fold change in either acidity or alkalinity. So pH 6 is 10 times more acidic than pH 7. 5 is 100 times more acidic, 10 times 10. And pH 4 is 1,000 times more acidic, 10 times 10 times 10. So once we get away from pH 7, either direction, it changes very, very rapidly. Go ahead. And the pH is just an abbreviation. A chemist would express the hydrogen, the ion concentration with those terminologies, so we just shortcut it and we call it 7, okay? Next. So how many are we talking about? Well, when we measure soil pH, we take about 15 mils, about 3 teaspoons of water, about 3 teaspoons of soil, and in that solution, I found a reference. There's about 903 trillion hydrogen ions. So we start talking about fairly large numbers. So anyway, not that that has a lot of bearing on what you're doing, but I just thought it was an interesting fact. Okay. So as we look at pH, we call it, or I call it, the soil thermostat. And a thermostat can regulate activity. So if I went over and grabbed the thermostat and I turned it up to 90 here in this room, the jackets would go after a while. You might start nodding off and sleep. I go and turn it down to 50 and the jackets would come back on, whatever. So that thermostat regulates the activity. pH regulates the activity, the chemical activity of all kinds of things, phosphorus and zinc and iron and what have you. When we look at, stay there for a second. When we look at soil pH, a fairly good range is 6 to 7.2. And if we get 7.2 or higher, we start seeing some problems because the chemistry of the soil changes and so soil nutrition changes. I call this the warning zone, pH 6 to 5.5, and then 5.5 or lower, we can start to have some growth problems. Okay. I went through the last 2 years of samples that we sent in from Iowa. It's about 45,000 samples. And I broke it out and wound up, we had about 15% of those in the warning zone, or in the problem zone, about 30% in the warning zone, about a half were in the green, the good zone, and then there were 10% in the high zone. The little pie charts there are data broken down by crop reporting district. And if you look at them, it's pretty similar. This is the overall average. Those are individual areas. And so it's pretty similar. I was sort of surprised across the state because you'd expect maybe some differences. But it looks like everybody's got kind of the same problem. Okay. Now, where did this come from? And this goes back to the northeast Colorado. It comes from primarily, now there are some natural causes that because of precipitation and what have you, that we see acidic soils in the higher rainfall areas. But modern agriculture and our use of nitrogen has accelerated that pH problem. So as we look at this nitrification process, when we convert not so much organic nitrogen, manure, or even soil organic matter, but when we're using urea, we're using ammonium, anhydrous ammonia, when we're using ammonium and urea in liquid 28 or 32% solution, what happens is eventually there's some chemical changes. We come to the ammonium form. There's a conversion, bacterial conversion, and we end up with nitrate. Now, nitrate is the preferred form of uptake by roots. Now the plants can take up a little bit of ammonium, but it takes a lot more energy. The nitrate flows with the water. As the plant takes up water, it takes up nitrate. So it's easy. But as in that process, we shuck hydrogen ions off that ammonium ion. And over time, as we increase nitrogen rates, we're getting more and more of those hydrogen ions build up. Just a rough rule of thumb, a pound of nitrogen, in order to neutralize the acidity from that, takes about 2 to 3 pounds of ag lime. So you can see over 10 or 20 or even 30 years how that adds up. So that's our challenge. Switch gears just a little bit, and I want to talk about aluminum. And where does aluminum in the soil? Well, if you look at clay mineralogy, most of our clays, actually they're layers of 2 silica layers, and they have an aluminum layer in there chemically. And it looks kind of like this. But if we look at some of our soil types, there's a lot of different soil minerals, but most of ours are in this upper category here, montmorillonite and illite. They're about 10% aluminum. Bauxite is where we get our commercial aluminum from. There's huge beds of bauxite, and that's refined and processed, and that's where we get aluminum foil and extruded aluminum, what have you. So what happens is as our minerals weather and wear down, we release some of the free aluminum ions into the soil. Okay, it's just a natural process. Okay. Now, where does pH fit into that? And what I've done here is I've tried to put together some research and some information from different experiments I've found to do some illustration. These two, one's from central Oklahoma and one's from one of our customers in southwest Kansas. So as we go from pH 6.2 down to pH 4.6, you see that free aluminum level increases. And it increases, once we hit pH of 5.5, again, you remember acidity changes very rather rapidly. At 5.5, we kind of see that aluminum number take off. Okay? So what's the problem? Why bring that up? Here's a picture of two different wheat seedlings. And genetically, the tolerant variety can kind of prevent aluminum from entering the tissue, and the sensitive variety cannot. Okay, so we look at a real problem, a real difference in that root growth. Now this is pH 4.3, it's grown in a hydroponic solution. Okay. Here's where the problem comes in. That free aluminum affects the meristem, the growing point of those root systems. So there's that old commercial of, here's your brain, they crack the egg, and here's your brain on drugs. Well, here's your root system, and here's your root system on aluminum. And what happens if you think of, and we're talking about root hairs, really fine root hairs, you can just barely see them. They have a root cap, a hard root cap, and they push through the soil. And if you can think, plants don't grow, it's not like shoving a garden hose through the soil. If you were to look closely in that garden hose, right behind the metal, the threaded section would be the growing point, the growing cells. And those cells stretch and reproduce and stretch and reproduce and stretch and reproduce. So if you damage those cells, the root system quits growing and you get something that looks like this. And we can get aluminum toxicity, and we get it below pH 5.5, and what we see is the roots look burnt. Looks like you took a root, instead of being that nice white color, they're kind of yellowish, maybe brownish. It almost looks like you took the seedling and took a cigarette lighter and toasted them. They also, above ground, looks like they don't grow properly. They look kind of flat and squatty. And a common symptom of aluminum toxicity is what looks like phosphorus deficiency. And I say it's an apparent deficiency. It's a plant deficiency, but not a soil deficiency. If we think about kind of basics in the soil, as our soil minerals break down, in this case phosphorus, it releases those ions, those single molecules or atoms into the soil water, because our soil water is really a soup. Our plants drink their food, they don't eat it. So they get their nutrition from that soil water. So if that soil water is in contact, or the root grows and can absorb those from the soil water, it'll translocate it and develop plant tissue. So if you have a damaged root surface like this, you're simply not going to get uptake. So you can have a high soil test, a very high soil test, and still get purpling, and it looks like a phosphorus deficiency. And again, it's a plant deficiency. There was somebody I knew that worked on this. He said you could actually take, one time he looked at a microscope at the root system, and you could see phosphate crystals, aluminum phosphate crystals in the outer edges of the root system. So those crystals, aluminum phosphates, are very insoluble. So even though it got into the plant, it was not translocated. So this does cause obviously some growth problems. Here's a couple of examples I want to show you. This is an old, back in the 80s, early 80s, there was a wheat variety that was grown in Kansas and Colorado. It's called Newton. About 90% of the acres in Kansas were planted to Newton. It was very sensitive, as time told us, very sensitive to soil acidity, and that's where the problems started rising. And so what you're seeing here is what we call exchangeable aluminum, the free aluminum, and yield. We see it does okay for a while, and then it just crashed and burned. And Newton was taken out of the picture early on. This was actually from Oklahoma, and the top graph shows you that same graph showing you the free aluminum. And this is showing a sorghum yield. And here we go at pH, go ahead. At pH 5.5, we see that aluminum take off. Well, look what happens to the yield. It starts dropping off, okay, for the same reason. You start getting the damage showing up, okay? Now, there is, you showed, earlier slide showed tolerance and sensitivity. Genetically, plants can, certain genetics can block the uptake of chloride or iron or whatever. So the aluminum toxicity and aluminum sensitivity, wheat breeders in Kansas and Colorado and Oklahoma, that's an important consideration. That's one of the things they look at in the breeding program. Now, we don't see it so much necessarily, I mean, Pioneer and those folks, they're not specifically breeding for aluminum tolerance, but that's all part of the yield thing. If something yields well, it most likely, if it's in an Iowa or a nursery here in the Corn Belt, it's probably going to do pretty well. Soybeans, we look at iron chlorosis tolerance, but the same thing applies. It's another metal tolerance. So there is some genetic thing. In corn and soybeans, again, that's kind of built, it's in the background. But if we have low pHs, we can still have problems. We can still have that aluminum toxicity issue. So it's something that's genetically. So what can we do? Okay, we can use ag lime, and this is the definition of ag lime. Any material, and there's a lot of byproducts and what have you, calcium, magnesium, in forms of reducing soil acidity, and here's key, carbonate and oxide forms. There's a lot of calcium, magnesium compounds out there, but you've got to have carbonate or oxides in order to adjust acidity. So very typically we get our quarry limestone, and we talk about calcitic limestone, which is primarily calcium carbonate. Some people call it white lime. Dolomitic limestone means there's some magnesium carbonate in there as well as calcium carbonate, and red lime is the terminology. You get some water softening. Some of the municipal water treatment plants, they soften the water. That sludge can be used as a liming material. You can use eggshells. They're not great, but it can be used. The chickens have deposited the calcium carbonate in the shell. So do we have good lime and bad lime? Well, state laws define lime quality, and you want to look it up here. This is what you would find in the Iowa Code of Regulations. So Iowa, there's a term called, you'll see a quarry will have to, if it's selling a liming material, it's going to have to give you a number, ECCE, effective calcium carbonate equivalent. Now you go west, it's ECC. You go south, it's ENM. You go north, it's ENP. And you go east, it's RNV. All right. These are all different terms, and each state has its own specific regulations defining that. Different terminology and slightly different things, but primarily it's a way of addressing lime quality. And in any case, there are two things that have determined the effectiveness of a lime source. One is the chemical purity, and two is the fineness. Now, what we're talking about in chemical purity is what is and isn't lime, because we've got in a lime, well, let's take quarry lime, for example. We've got some limestone, we've got a little bit of moisture, you're going to have some sand, dirt, whatever, and we're looking at the carbonate content. Now, we don't care if it's calcium or magnesium, that's a whole different argument, but we're looking at carbonate content. We do that by titrating with acid. We take a lime sample, add acid to it to determine the carbonate content. Okay, and then again, that's specified in the code. Then we look at particle fineness, and that is done with a sieve analysis. Now, Iowa, we use a number 4, number 8, number 60. Each state has a different set. Nebraska uses, and Kansas use 8 and 60. Missouri, you throw 40 in there. So each state defines that. But what we're trying to do is trying to separate out and get some idea of the relative particle size. We want to see what percentage or how many fines we have, how many medium-sized particles we have, and coarse particles. And then, again, by regulation, there is an effectiveness assigned to that particle size or that range of particle sizes. But what we're trying to get at is we expect the fine lime sources to last, to be effective, to do their thing in a year or two. The medium may hang on there to 3 to 5 years. and the coarse particles, it may take more than 5 years to do. But again, this is all defined by administrative code and by state law. So every state has its own set, but they're all rather similar. Okay.
Sludge lime, how is it rated for fineness? Because
very fine. Yeah, typically sludge lime is really high in fineness because it's.
Yet it's hard to spread because it's chunky, clumpy.
Well, that's part of the problem with lime. Depends how it's processed, because they'll pump that lime out or that, and let it dry. Once it dries, the individual crystals are fine, but they'll get in chunks in there. Now, if you can break those chunks up, and that's the thing. Quarry lime, it's no different. You can take road gravel and ag lime come out of the same quarry. Okay, road gravel is just processed less. To get ag lime, you got to run it through the grinder. So it's a mechanical step. So you've got some more expense in doing that. So fineness of grind becomes an important consideration. And I'll give you an example here. I just did the math here. Let's take a little block of limestone. It's a cubic inch. It's got 6 inches of surface area. We got top, bottom, and 4 sides. If we cut it in half, now we've got 8 inches of surface area because we've opened up 2 more square inches inside. So every time you cut it, you open up 2 more inches of surface area. So we ran the math, if we cut it into 1/8-inch cubes, we've got about this much surface area. 60th, we got about, maybe about like this. But we get into 200, the really fine lime, now we've got almost a square yard of surface area. And so that's what the fineness has to do with. It's the surface area that's available to react with the soil. And so the finer the lime, the more surface area, the quicker it's going to act. Okay. And I say it's always like starting a fire. You got twigs, kindling, and logs. Fines are the twigs, medium is the kindling, and logs are the coarse. Okay, so we have a test. We do lime quality analysis, and this is what the lab data looks like. So I pulled one up from Iowa. Go ahead. And it's about 95% pure. So we got a lot of lime, and then break out the particle sizes. So we got a few coarse particles. They're larger than 8. Some medium particles, and we have a number of fine lime particles. So we're kind of going toward the lime. So we do the calculation here, and we take the purity times the fineness factor. We've got about 64% ECCE. Derek pulls a sample, recommends 2 tons of lime, and the samples, we express it, not every lab does this, we express it as 100% pure lime. So what we have to do then, we have to take that 2, divided by our ECCE, that gets us 3.1. If we want to take the moisture into account, now we're to 3.6. So in order to get our 2 tons of ECCE lime, we've got to apply 3.5 tons of product. So that number becomes really important in the making a recommendation. Now, how much do we apply? We have to go back a little bit to soil chemistry. I talked about our clay minerals have aluminum, so that really the soil chemistry also have hydrogen ions, but this is a residual acidity. So this breaks down, and what we do is on the surface of the exchange surface, you see the lab data, the CEC, cation exchange capacity. That's what we're talking about here. It's the surfaces of the clay particles, and they're able to hold positively charged ions. So hydrogen ions are positively charged, and so they're, if you could look in a not even a microscope, but you'd see this cloud of different things around that clay particle. Some would be hydrogen, some would be calcium, some would be ammonium, and what have you. And then there's a certain amount, a smaller amount, is actually out in the soil solution. So the soil water, that's the term I use it. So we break this out, we're saying bound, potential acidity, and active acidity. Now, we can neutralize the active acidity with just a few pounds of lime, not a handful, if you will. Well, once we neutralize that, some of the hydrogen ions move out into solution that nature tries to establish an equilibrium, so you got to have a few more pounds. Neutralize a few more pounds and a few more pounds. So what we want to do is, yeah, we can neutralize this fairly easily. We want to know how much reserve acidity there is. So that becomes important. So here's what we do in the lab. I get the question a lot, why do we have 2 pH numbers on the lab report? Well, here's what we do. We take water and soil, we make a slurry, use electrode to read the pH, and report that as what we call the soil pH. Some people talk about water pH. Now, if that pH is greater than or equal to 6.2, we're saying it's down, yeah, we're getting close to that warning zone. What we do is we add this buffer solution, and it's at pH 7.7, so it's an alkaline solution. It's kind of a liming material. We add it to that sample, wait 30 minutes, let it do its thing, and then we report that buffer pH. And so the difference between 7.7 and what the buffer pH is determines, there's a calculation we use to give, and I'll say it's an estimate of the amount of lime, because there's, nature's not perfect. How many tons of lime would be required to bring that soil pH up to our target, 6.0 or 6.5 or whatever we're looking at, okay? So the quick way to, go ahead, think about this, those 2 numbers. The soil pH, the question is, do I need lime? The buffer pH, how much do I need? If that's blank, we shouldn't need it. Okay, so that's the quick, that'll be on the quiz after the presentation. Go ahead. Oh, all right. Well, now the question is, how fast will it work? And I bring this up because this year, it seems like we've had a lot of questions about pH and liming and such. So what I did was I went through and assembled some research studies and tried to take a look at that. So the first one here, it was an Iowa study, taking a look at some different lime rates. And what I'm looking at is how fast do we get up and kind of start leveling off, because that tells me we've hit the maximum point. So go ahead. So in Iowa, this particular study, 5 to 12 months. Here was another study in Iowa looking, and the dots are, the round ones are actually lab grade calcium carbonate, and the squares are ag lime. So we got 4.5 months. Yeah, it's done its thing. And after 12 months, we're almost there. So Oklahoma, this is the same rate study. We look, we get up to that, depends on where you're looking at, about 4 months, and then again at 18 months. And this was in Nebraska. This is actually an on-farm trial, and looked at over a period of actually 6 years, but after 12 to 36 months. So the take-home point is we probably, it may occur faster, but we should be seeing a change in pH after about 12, a year later. So if you go out right away or fairly soon after, you may not be seeing the complete effect of that liming. Now we know how long is it going to last. This was a study in Kansas, couple locations. This was long-term no-till, different lime rates. And go ahead. And looking at it for 3 years, year 1, so we've got lime rate and we've got yield. We've got wheat, corn, and soybeans in the 3 years. And we're still seeing an effect of the lime after 3 years. Now at the low lime rates, we're starting to see it kind of drop off, not making a difference. But 3 years in this case, okay? This was an Iowa State study. They looked at, it was 43 site years, and these were on-farm, they were strip trials. And the either had lime or no lime, and the dark bars are what we see after 4 years. So we're seeing that there's still an effect on yield after 4 years until we get down here into the 6.0 range, 6.2. And if we get an alkaline soil, we can actually maybe do some damage by putting lime on. We can over-lime and create some problems. So this was a on-farm research. This is in Washington County, Nebraska. It's just kind of across the river from Council Bluffs. Looking at 14 years and corn and soybean rotation. And if you look at this, the white bars, what they did was they looked and they applied statistics to it. It's replicated. So the white bars, even though it shows what looks like an increase, the problem is there was just enough going on with the weather and such that they couldn't quite be sure, was it the lime doing the job or was something else in effect. But out of this time, we had 7 years where we saw, 7 out of 14 where we saw an effect from the lime. And the thing that surprised me is year 14, we're still seeing some effect. So the lime, may last long. Here was this one was a similar study. What they did, they compared lime and they had a no-till situation and a double disc plant and trying to say, okay, is tillage or lime going to do the job? Well, with the tillage itself, the first year, tillage was responsible for an increase in yield. Then, never more. The lime by itself, when they sorted that out, we had 5 years out of the study where the lime had an effect. And then we had 1 year where the tillage and the lime had some effect, incorporation. So the issue there, I think, is get the lime on. Tillage may be a little bit secondary. This is going back to that K-State study where they were looking at no-till. These are 2 different fields, and they took inch by inch, took soil samples. And here at the top 3 inches, we were below that critical level of 5.5. Now, we were able to see it was no-till, so there was not, the lime was not worked in. We were still able to see an increase or an effect on the yield. The reason, and just a second back up, the reason in the no-till field, probably what happened is we were using either, I don't know what they were using, urea or liquid nitrogen. They were broadcasting it. So as that is dissolved and kind of moves in the soil, we get those ammonium forms of nitrogen converted over into nitrate, and then the nitrate can be moved farther down the profile. But that conversion is taking place in that very soil surface. So we develop kind of a hot zone here in the top. And in thinking about no-till, because we've had I think I've had this discussion with a couple of you anyway. As I think about it later, lime is not soluble. We were talking about the treatment lime. You can't dissolve lime like you can sugar or salt. But I think maybe what was going on here was in a no-till situation, we're not working the ground, and what we've got is old root channels. We got a lot of holes in the soil. And I think what we're getting is maybe just the fine particles are actually being physically moved down into the soil profile. And so they're reacting and they're having an effect. So what this is telling me is that get the lime on and maybe, don't worry about the incorporation right away. That may or may not be as important as we think. Just getting the lime on. It's okay now. And then bringing that up, we do run into a situation in areas we talk about soil stratification and layering. Go ahead. Here's one of our customers pulled a sample. Now this is a long-term, and I don't know a lot about the history, but it was a long-term strip till, not a no-till, but a strip till situation. So pulled a 12-inch sample, got a pH of 5.9, phosphorus level of 32. That's pretty good level. Okay. But when we broke it down in 3-inch increments, the top 3 inches we had a pH of 5.1, we went to 6.7. Our phosphorus level went from 77 to 6. So even in that strip till, we were developing a layer, a hot layer here in the surface. Now, hot when it comes to pH and hot when it comes to phosphorus, okay? Well, here's the problem. When we plant, we're planting corn, we're putting it roughly 1.5 inches deep, depending on what you're doing. We're putting that corn, whatever you do, is right in that hot zone. So we got great fertility in there in terms of phosphorus, but we also have the potential for aluminum aluminum problems. Now, this may not be, in this situation, may not be a disaster, but as I think about it, what we've got is, if we've got aluminum here, we're damaging some of those young roots. Those roots are trying to grow trying to grow out of that layer. Once they get out of that layer, they're probably doing okay. But initially, there's some damage there. Even though we've got a lot of phosphorus in the soil, high soil test, those roots probably aren't getting the full benefit of that. Now, is it a disaster? Well, not necessarily, but if we think about it, is there a day or 2 day delay in emergence? Are we getting erratic emergence from that effect? I know, what's his name? Randy Dowdy, the guru from Georgia, he's big on that, getting them all to emerge on the same day. And there's a lot of logic to that, so that may be what's happening. I use anhydrous ammonia, so that's not a problem. Well, this is an Iowa study, and this is years back, actually from about 1990, and it was a ridge till system, so they didn't have an RTK, but they were riding on the ridges, so they were putting the ammonia in the same place. And it's a little hard to see the numbers, but these reddish areas are all below 6. Right here, this is 5.1, and so that bright red spot is below 5. So we're putting on nitrogen, we've developed an acidic zone in the soil, and so we've got roots that are trying to grow into it. It's going to be harder and harder to take it up. So we can get the stratification vertically and horizontally. One of the things about it is, and we've talked about this, is it might not be a bad idea every so often to take a 3-inch sample. We advocate taking your regular 6-inch, 8-inch sample to maintain the soil history. But just every now and then, like on a grid sampled field, for example, maybe take every 10th or 12th sample, take a 3-inch sample and just check for pH and see what's going on there. Because if you've got that stratification, it's important to know about that so that you can deal with it. Now, you want to take, like I said, your regular samples to keep that soil test history going, but just spot check that surface. Here's something that raised a lot of questions. We've had this discussion several times. This is the drought monitor map from a year ago, okay? And I guess that's the heart of Iowa, but we had some pretty severe drought. Where drought comes into play with soil pH, this is, the graph over there is, it's actually from Kentucky, and they had a long-term drought in a part of the state, and Dr. Sikora looked at the county average soil pH versus the Palmer Drought Index. And we went from 6.5 to 6. We dropped the soil pH by half a unit. And we've seen that in lab over and over again. When we have a drought, not just a dry spell, but a regular drought, we can see that soil pH drop by half, not uncommon, 0.4, 0.5 units. In 2011, now Iowa and Nebraska and whatever, the severe drought happened in 2012. And if you were farming in 2012, you know what I'm talking about. It was pretty severe. Now, in 2011, we had a drought, but it stopped about I-70, which cuts Kansas in half about north to south. We had some of our customers in the Texas Panhandle were seeing 0.6 and 0.7 unit drop in pH. And so there was kind of a panic there. And it has to do, and I'll explain, it has to do with weather. So the typical answer we gave before, well, just hang on, don't put on the lime yet, wait till next year, wait till you get some rain. Okay, so that's what happened. And here's why. Go ahead. We measure pH with this glass electrode. And the salt content of the water solution has an effect on pH. And it's, I don't know, you can get into physics and what have you in there. But this was a diagram somebody put together looking at low salt content solution, a very high content or high salt content solution, and we went from 6 to 4.5. So this is what's happening in those droughts. We get soluble. It's not something you typically would measure. We do measure it in some of the our drier areas, but those soluble salts. We get our soil minerals. The soil dries out, and sometimes you see that little white crust and such. That's what we're measuring. So we actually, the soil, because the soil's drier, the salt content tends to be higher, and that tends to depress, that affects that pH meter and tends to depress it. Go ahead. This is, I ran across this that somebody had put together, and that was a specific salt content, and it was equivalent to 150 pounds of nitrogen and 120 pounds of potash. And we took our soil pH from 6 to 5.5. Where I ran into that was I was listening one time to one of the Hefty Brothers podcasts. And the Hefty Brothers they like potash. And one of the brothers was saying, well, you know, I put on 300 or 400 pounds of potash, and I saw the soil pH drop. I didn't know that potash would acidify the soil. Well, it really doesn't. We were seeing this kind of an effect there. So that's a real thing. Now, one of the things we've done is there's Sikora. Dr. Frank Sikora is at University of Kentucky, and he developed this buffer solution. In soil testing, if you develop something, you get to hang your name on it. So we typically have used what's called the Sikora solution, and there's a modification that we call the Sikora 2. And for the most part, it does, you know, it's equivalent, it's equal to the Sikora 1, if you will. But in other situations, we do get some differences. And one of the things, it tends to mask this salt effect. And so we might get a different answer, but we think it's a better answer. And so we've had, you know, a lot of guys are switching to Sikora 2 just to overcome this. Okay? Now, what happens when the lime doesn't work? Okay, I put my lime on and didn't see a change in pH, you know, what's going on? This is a K-State study, and now this is only 6 months after application, so maybe we don't have it. But if we look, go ahead, slide. If we look at the check, they were looking at lime rates and looking at ag lime, Pell lime, pure lab carbonate, and then lime of different sizes. We had pH of 4.5, and we really didn't bring the pH up as much as we would like to. So the pH, you know, did the lime work? You know, what's going on? Okay. The same study, they looked at the aluminum in those same samples. Go ahead. And if you look, we started out with 94 parts per million aluminum, which is a problem. But even though we didn't change the pH that well, we dropped the aluminum out of the solution. And this makes me think about, you know, that one study, it was 14 years later. Well, I'm not sure what the pH was done, but maybe that those coarse lime particles were actually having some impact on the soil aluminum. So that's one of the things. That's a separate test. It's not a test we normally do, but that's something that can be checked. And we've had some situations where the lime didn't work, but we did a with and without with the aluminum, and it solved the problem. So anyway, that's one of the things to keep in mind. This aluminum, it's not something you're going to be thinking about every day, but it does have an impact in crop production. Well, what about the pelletized lime? We get questions about that. This was an Iowa State study. It's kind of interesting. They 6 locations, 2 years, so fairly extensive. They compared ag lime to Pell lime to pure calcium carbonate and looked at it at different rates. So these are the graphs for 1 ton, 2 tons, and 4 tons of product. Now, the top line is the Pell lime, the second lime product is ag lime, and the third line is the check, no lime at all. And if I sell Pell lime, I'm going to hang my hat on. I'm going to show this off to people. Okay, so what's going on here? Well, I did a little. You had to dig a little deeper into the study. Go ahead. And the 2 tons were played on CCE, just the calcium carbonate equivalent, how much pure lime there was in the sample. And if we look, the carbonate, ag lime was 95, Pell was 94, calcium carbonate was 99. But when you looked at the fineness factor and did the math, we now had 59% ECCE, 92% and 99%. Go ahead. And when we compared ECCE, based on that, the ag lime after 12 months, ag lime and Pell lime matched up. Even the lab-grade calcium carbonate based on ECCE. So that's a really important number. There's nothing magic about any lime source. It's strictly based, look at it on the basis of the, look at the purity and look at the fineness, the effectiveness. Those two factors are important to determine that. So go ahead. What about putting it in furrow? I ran into this study, this is actually Oklahoma State. This was on wheat, 4.9 pH. What they did was they broadcast ag lime, and then for 2 years they put 200 pounds in furrow every year, and then 2 years later they sampled, 2 and 3 years later they sampled after harvest to see what it looked like. And this is a grid sample. If you can see it, it's a 4-inch by 8-inch grid, and they took some really fine samples. Go ahead. And they created this grid map for a 4-inch by 8-inch grid. So here's our control with no lime. The 6-inch pH was 4.7, so we can kind of see where, right there in the furrow, it's the blue color is more. There's a scale here. 5.8 above 5, but we've got our hot zone. Now we added the total of 400 pounds of Pell lime, and we're seeing a little bit more activity right there where the wheat seed is placed, but our pH is still only 4.9. Our ag lime, we're doing more good. We're getting a lot more effectiveness, and we're at a pH of 5.3 in a 6-inch sample. And this is kind of what it looked like, or this is not kind of, this is what it looked like. The wheat with only 200 pounds of Pell lime versus 2 tons of ag lime. And the reason, you see, even after 2 years, as they were digging, you can still see the Pell lime was still sort of intact. And this is the issue with Pell lime. It's really fine, it's really high quality, high ECC, but unless it's worked in, that pellet will stay there. It's certainly going to have, right around that pellet, it's going to have an impact on pH, but in between the pellets, it's not moving, it's not having an effect. Now, Pell lime has it, there's nothing magic about it. It's not more effective than ag lime. Take a look at, you've got to look at the ECCE. What about to maintain pH? We've had that. Again, the primary reason we're developing acidity is that nitrification process, getting hydrogen. And it takes about 1.5 to 2 pounds of ECCE lime per unit of nitrogen. So if we put on that 200 pounds of Pell lime, we're putting on 190 pounds of ECCE. We're offsetting the acidity from 100 to 125 pounds of nitrogen. Okay, so that's fine. But if your nitrogen rate is higher than that, you're long-term, you're potentially developing more and more acidity. And here's one of the issues. One of the sources of acidity long-term, and this is why we see acid soils develop in the higher rainfall areas. When we have higher yields, we're pulling more calcium and magnesium stuff out of the soil, just carrying it off as a crop. And we kind of, it's like we're leaving more room for the hydrogen ions to get that reserve acidity. We're emptying out parking spaces on that clay content. So as we increase our nitrogen rate, we are increasing the hydrogen ion rate, so we're adding to acidity. We are increasing yields, but we're also removing some of those cations, and so it's kind of compounding. The primary reason is because of the nitrogen application, but our modern farming, just the fact that we're increasing yields and nitrogen is a driver of yield increase, we're going to acidify the soil. Now, some soils it's not going to have much impact, some soils it's going to have a lot of impact, but that's where our soil sampling and long-term monitoring comes in. So just kind of summarize here, these are questions that, as I was putting this together, okay, what questions have I had, do I get on this? So why those 2 pH values? Remember, we got soil pH and buffer pH. Do I need lime? How much lime do I need? What product? Okay, we've got to look at both the purity and the fineness, check the label, whatever label it is, and look at cost. If you're comparing lime sources, what's the cost of ECCE? That's a pound of a pound of lime is a pound of lime, so to speak. Now, is, maybe more or less available. You got to look at transportation, that sort of thing. Is it convenient to apply? I mean, those are individual factors. Pelletized lime, I'd say partial pH maintenance. If you've got a really highly acidic soil, a few hundred pounds of pellet lime is probably not going to have a long-term effect. Short-term effect, maybe. But if we get, if we get our ag lime, if we can get the pH build up into that, 6, 6.5 or whatever, yeah, we may be able to use pellet lime to maintain. But here again, in order to maintain, it's important to track and monitor that pH and see what's going on. How much? Well, depends on what crop, what's your target pH. Certainly we want to get above 5.5, 6, maybe 6.5 is better, but at least get it up to 6. And again, we need to adjust the recommendation for that quality of that ECCE. Okay? Now, how fast will it work? Well, 6, certainly 12 months after we put it on. And it may not change the pH, but it may have an impact on that exchangeable aluminum. And if you have a question about that, it is an extra test, and it's something we can do and get an idea. And then how long will it last? Well, certainly 3 to 5 years, but it may have an impact for a longer period than that. So you need to take a look at that. And then, again, how much do we need to work it in? Well, we could discuss that a lot, but getting the lime on, just getting it out there, that's the priority. Worry about the incorporation, what we're doing later on. And how deep is our acidity? Are we talking about 3 inches, 6 inches, or deeper? It becomes important. So with that, I appreciate your attention.